Alright, we're going to go ahead and get started with Unit 11 on acids and bases. This is a fairly lengthy unit and a very important unit for both the AP and the IB exam. In the first lecture, we're going to talk about the theories of acids and bases. We'll look at both kind of a historical approach as well as looking at our modern ideas of what acids and bases are and their characteristics. The essential questions for this lecture are: what is a Bronsted-Lowry acid and base? How do you determine whether or not a species could act as a Bronsted-Lowry acid and base? How do you deduce the formula of the conjugate acid or base of a Bronsted-Lowry base acid? And finally, what is a Lewis acid and base? So all of these questions will be addressed in this lecture, and you yourself need to be able to answer these for the quiz over lecture 1. Alright, so let's get started. We're going to first look at one of the most earliest known theories of acid and bases, and this is called the Arrhenius theory. All that is expected here is that you have somewhat of an idea of what the Arrhenius theory is, because it is this theory that's going to help us to expand our understanding into more or less the modern or current theory on acids and bases. So to begin with, we can look at the Arrhenius theory of an acid is any substance that when dissolved in water increases the concentration of H plus ions. So I'm going to give you an example of this. Say you have HCl, and we are going to dissolve HCl into water. And when we do so, we will create H pluses and Cl minus ions in a solution. And the more H pluses that are produced, the more acidic our acid is. And so HCl is considered an acid because it's making more H pluses. So what about bases? Well, according to Arrhenius, bases are anything that when dissolved in water will increase the concentration of the OH minus ions or hydroxide ions, such as sodium hydroxide. Take sodium hydroxide, we dissolve it in water, and we get out sodium ions, but what's important is the hydroxide ion that is made. And so, because sodium hydroxide makes a lot of hydroxide ions, we consider it a base. Again, the importance is producing the H pluses and the OH minuses for the Arrhenius acid-base theory. Alright? So, keep that in mind as we go into more and further into our conversation here, discussion on acids and bases. The one thing to make note of is that an H plus ion is simply a proton, as you'll see here in our next slide. So before we move into more of the modern theory of acids and bases, we need to talk about the hydronium ion. The hydronium ion is very, very important that you know the formula for it and how the hydronium ion is made. So again, as I just mentioned, to think about is that an H plus ion is simply a proton with no surrounding valence electrons. You think about what hydrogen is. Hydrogen has one proton and one electron. And when you remove that one electron to form an H plus ion, the only thing that remains is a proton. So what I want you to think about as we go through this lecture is that H plus is really a proton. Right? Now, when an acid, an Arrhenius acid, dissolves in water and creates more H pluses, what we now understand is that the water molecules are going to actually attack those protons or those H pluses, and when it does so, it's going to form what is known as the hydronium ion. And the structure you see here is the hydronium ion structure. To make it simple, we just go at H3, 0, or O plus. Alright, that's the hydronium ion. So, making it look like our chemical reaction has occurred, let's do our HCl. We have HCl, and it's going to dissolve in water to form H plus ions plus the Cl minus ions. But what's going to really happen is that water, and what makes this work so well is that water has lone pairs of electrons. And those lone pairs are important, as you'll see later. They're going to attack the H plus, and in the result is going to form the hydronium ion, like so. And so when we put this all together, erase this, what we can really say that's going on is that the H plus ion, the HCl acid, remember HCl is our acid, in the water, which has these lone pairs, is going to actually make the hydronium ion plus our chlorine ion. And so this is what's really occurring with the Arrhenius acid idea, is that instead of the HCl dissolving in water to make H pluses, it's actually reacting with the water to make the hydronium ion and the chlorine ion. Alright, so this is a really important concept for you to have down. Alright, so sometimes we don't use the hydronium ion, we just say we have H pluses, but in reality is that we don't have the H pluses, we really have the hydronium ion. And so we're going to use the hydronium ion most of the time. Alright, so now let's get into more of our modern idea, the Bronsted-Lowry acid and base theory. Now, as we begin to understand what happens with the H plus ion, that it's actually being attacked and reacting with water to form the hydronium ion, Bronsted and Lowry, independent of each other, begins to develop a more perfect picture, you could say, of what an acid really is and really what a base is. And so by the time Bronsted and Lowry both published their work fairly much simultaneously of each other, their work was immediately accepted, and therefore they named the theory Bronsted-Lowry after their contributions of what they've done with acid and bases. So what exactly is the Bronsted-Lowry acid-base theory? Well, these two are the important points here. An acid will transfer H pluses to a base or a proton, or in other words, an acid is known as a proton donor. Alright? Whereas a base will accept H plus ions from an acid, and a base is going to be known as a proton acceptor. Alright, now we just saw this with forming the hydronium ion. So we said that HCl, I'm going to draw several things here, HCl is an acid, but because water is accepting that H plus, because it's literally like attacking there, and accepting the H+, we're going to say that the HCl is the acid because it's the proton donor, and water is the base because it is the proton acceptor. And it forms our hydronium ion plus our chlorine ion. Alright? So what we have found is that when we have a Bronsted-Lowry acid and base, we always have a Bronsted-Lowry acid and base. In order for us to have an acid, we must have a base, because the acid always donates an H+ ion or a proton to the base, and the base always accepts it. Alright? Now, one of the categories, or one of the things that the base has to have in order to accept an H+, is it must have a lone pair of electrons. That is critical for you to understand. All bases, in order to accept a proton or an H+ ion, must have at least one lone pair. And water, because it has its lone pairs, two of them, it's able to accept the H+ from acidic acid, and in this case act as a base to form the hydronium ion and the chlorine ion. Alright? So, we'll highlight here, acids base reactions involve the transfer of H+ ions from one substance to the other. Alright? So from the acid to the base. So I'm going to do a generic reaction. This is kind of a standard acid-base reaction that you can put into your notes. So acids are represented by HA, and bases by a B, and we have a lone pair that we'll put on the B. Alright? And so again, what will occur is that the lone pairs will grab a hold of the H+, so the acids will donate the H+ to the base, so our acid and base, and many times we will form an equilibrium situation with these, and so we will have HB plus A minus. Alright, so the A is referred to as the anion, and now the base has an extra proton, and so that's why it's a plus charge. Because remember that H pluses are really protons, and so now the base, adding that proton, is going to have a positive charge. And the anion, this is the anion, it loses a proton, so it becomes a negatively charged anion. Alright? And so that's kind of the way we look at this. So how do we determine whether or not a species can act as a Bronsted-Lowry acid and base? Well, the two things you have to look at. One is the acid has to be able to donate a proton, and the base has to have a lone pair of electrons, at least one, to pick, and it has to be able to pick up that H+ or that proton. Alright? So you need to kind of think about this, but that's pretty much the basic idea of a Bronsted-Lowry acid and base. Alright, so now what we're going to look at is what it means to deduce what is called a conjugate acid and base of any Bronsted-Lowry acid-base type of reaction. Okay, so first of all, I want you to note what the word conjugate means. The word conjugate means joined together as a pair. Okay, joined together as a pair. So what we have going on here is to always remember this simple thing. When acids react to form bases, and bases will always react to form acids. So again, one more time. Acids will always react and they will make a base. Where a base, when it reacts, it will always form an acid. And this acid forming a base is called an acid-base conjugated pair. An acid-base conjugated pair, and they just differ by one proton. So let's take a look at what we have here in this diagram. We have our acid. Actually, let me erase this. So we have our acid here, which is HNO3, and we're going to remove the proton, and it's going to be picked up by water, and water is going to be my base. And so the acid now becomes the base, and we form what is called the conjugate base. So HNO3, when it loses that H plus, now forms NO2 minus, and NO2 minus is now the base. Alright? The base, which was water, is going to pick up an H plus, and so now it becomes an acid, or known as the conjugate acid. So water being the base, and the hydronium ion here is the conjugate acid, and we have a conjugate acid-base pair. Right? We'll do more examples so you see this. So here's a different situation here. We have our base, which is going to be ammonia, NH3, and in this case now, water is going to be an acid. That's right, water can be an acid. It also, as you've seen, can be a base. It just depends, does water accept a proton or is it donating a proton? So in this case, it's going to donate one of its protons to ammonia, and so therefore the ammonia is now going to become an acid. We create the conjugate acid. Where the acid, which is water, it loses the H plus, so now the acid becomes the base. So what we're trying to say here is that the base, when it grabs a hold of a proton, it will now become an acid. And the base, the acid will lose a proton, and so now it will become a base. And so we form an acid-base conjugated pair. Right? Let's try looking at a few other ideas here. Alright, let's say we have a chemical reaction, or actually let's do generic again. So we have HA plus our base. Alright? So what's going to happen is our base is going to pick up the H plus, right? And actually I probably should write this the other way around, because in reality the lone pairs are going to attack the H plus. And when we do that, so this is our acid and this is our base. So if the acid loses this H plus here, loses it, then it's going to actually now become an acid, or A minus. So this is now, a base. My acid now becomes a base, or a conjugate base. So this is the acid-base conjugated pair. So we call this a conjugate pair. Alright? My base is going to gain an H plus, so my base now becomes an acid because it has an extra H plus. So this is the acid. Now, and this is the acid-base conjugated pair. Alright, so again we see that an acid, when it donates an H plus, will now become the base, and the base which picks up the H plus, now becomes the acid, and we form acid-base conjugated pairs. So let's take a look at some real examples. Some more. Erase all of these. Alright, so let's take a look at something like this. Acetic acid. So we have HC2H3O2. So this is going to be my acid. My base, let's do water. Right? Water is going to be my base. And water, of course, has to have a lone pair of electrons to even act as a base. So my base is going to attack my H plus, which is sitting right there. And the base now is going to grab another hold of that and become a hydronium ion. And the hydronium ion now becomes my acid. Right? So we have our acid-base pair, conjugated acid-base pair. Again, the base becomes the acid, and my acid now becomes the base because it's going to form C2H3. Well, I'm running out of room, so let me rewrite the base down here. Plus my base plus is C2H3O2 minus. So that's my base. And the oxygen here has some lone pairs on it, so that's going to be able to accept an H plus. Alright? So I'm hoping you're getting this idea. Erase this some more. Alright, look at some other examples here. Alright, let's say we have let's say we have a hydronium ion, H3O plus. Okay? If this is my acid, then what is the base of the hydronium ion? So let's draw a conjugated pair of this. Well, if the acid loses an H plus, then let's get rid of one of these three, and what's left is H2O. So that tells us that water is the base and my conjugated acid-base pair of the hydronium ion. Right? Let's take a look at another one. Let's say we have ammonia. Ammonia is NH3. And we're going to say this is a base. And we know that ammonia, if you draw the Lewis structure, has a lone pair on the nitrogen. So it can pick up a proton. So if it picks up one more proton, then what will it become? Well, one more proton added is NH4 plus. And that it becomes my acid now. Alright, and that's my acid-base conjugated pair with ammonia. Now remember, there's only going to be one H plus difference. That's it, between the two. The acid should always have more protons than the base. And the base better have a lone pair of electrons. Alright, actually we can just... Alright, let's look at a couple more, and then we'll be done here. What about NO2 minus, right? NO2 minus. Let's say that NO2 minus is a base. So if NO2 minus is a base, then it picks up an H plus, then it would be HNO2. And it goes from a minus to neutral because it's picked up a proton. And so that becomes my acid. And there's only one proton difference still. Alright? So I'm hoping you kind of seen what we're doing here. The bottom line is that the base will pick up a proton and now it will become an acid. The acid will lose a proton, so now it becomes the base. And if you can just remember that, plus that there's only one difference between, or one proton difference between the acid and the base. And that's pretty much the Bronsted-Lowry acid-base theory, what we've done there. Alright, so we've gone quite a bit into this lecture, so what we're going to do is we're going to break this up into one more part. And so we're going to end part 1 of this right now, and then we'll pick up here in a minute on part 2.